Unit 6, Lesson 2 is on exponential models. So our lesson essential question is, how can you develop exponential models to represent and interpret situations? At the end of this lesson, you'll be able to write exponential models in different ways to solve problems. Example 1, rewrite an exponential function to identify a rate. In 2015, the population of a small town was 8,000. The population is increasing at a rate of 2.5% per year. Rewrite an exponential growth function to find the monthly growth rate. So I write an exponential growth function using the annual rate, the 2.5%, to model the town's population Y in T years after 2015. So 2015 is my 0 year, my start year. My initial population was 8,000. Then I have 1 plus that 2.5% changed to a decimal, 0.025, and then T is years after 2015. Okay, so I have Y equals 8,000 times 1.025 to the T power. To identify the monthly growth rate, you need the exponent to be a number of months in T years, or 12 times T. So multiply the exponent by 12 over 12 so that 12T represents the number of months. Applying the power of a power rule helps to reveal the monthly growth rate by producing an expression with the exponent 12T. So Y is approximately 8,000 times 1.00206, because I divided it, basically I raised it to the power of 1/12 to the 12T power. So the monthly growth rate is about 1.00206 minus 1, or 0.00206. So the population is increasing about 0.206% per month. All right, so let's try it. The population in a small town is increasing annually by 1.8%. What is the quarterly rate of population increase? Okay. So population's increasing annually by 1.8%. So I'm going to take that 1 plus 1.8. I'm going to change the 1.8 to a decimal. So remember, you have to divide that by 0 or move the decimal over, however you want to think about it. 0.018. And that's raised to the T. Okay. So 1 plus 0.018 is, of course, 1.018. Then I'm going to raise that value to 12 over 12 because I want to figure out quarterly. So quarterly, instead of 12, like monthly would be, quarterly is 4. So 4T over 4, which is like saying 1.018 to the 1/4 power is to the T. So that gives me 1.018 raised to the 1/4 power gives me approximately 1.0044694. And I need to subtract that answer. 1.0044694 minus 1 equals 0.0044694, which equals 0.45%. So quarterly, I multiplied that answer by 1/4, subtracted 1, multiplied my final answer by 100. They took it out to 3 decimals, so same quarterly rate. Okay. So concept, compound interest. When interest is paid monthly, the interest earned after the first month becomes part of the new principal for the second month, and so on. Interest is earned on interest already earned. This is compound interest. So up until this point, we've probably dealt with simple interest. So you're just finding whatever the rate is and then finding the simple interest of that, PRT, so the principal times the rate times the time. So compound interest is a little bit more complex because it's compounded. So the compound interest formula is an exponential model that is used to calculate the value of an investment when interest is compounded. So P is the initial principal invested. So it's the money that you put in. R is the annual interest rate written as a decimal. So 0.5%, 2%, whatever that might be. N is the number of compounding periods per year. So if it's quarterly, it would be 4, semi-annually would be 2, annually would be 1, monthly would be 12. Okay. A is the value of the account after however many years. Okay. So T is always in years. All right, so example 2, understand compound interest. Tamira invests $5,000 in an account that pays 4% annual interest. So annual 1, so 1 per year, 4%. Okay. Principal is $5,000. How much will there be in the account after 3 years? If the interest is compounded annually, semi-annually, quarterly, or monthly. Okay. So I use the compound interest formula to find the amount of Tamira's account after 3 years. Okay, so annually would be 1. Okay. Semi-annually would be 2. Quarterly would be 4, and monthly would be 12. Okay. So notice T here is 1, 2, 4, 12. So you're multiplying it by that same amount, that R amount, that N amount. Okay. As the number of compounding periods increases, the amount in the account also increases. Okay. So you can see that it goes up each time. All right, so let's try it. $3,000 is invested in an account that earns 3% annual interest compounded monthly. What is the value of the account after 10 years? So my formula is A equals P times 1 plus R over N to the NT. Okay. So I want 10 years, 3%, 3,000. So A equals my principal rate is 3,000 times 1 plus my percentage rate. So 3% as a decimal. So 3 divided by 100 or 0.03 over, it's compounded monthly. So that's 12 raised to the 12 times 10 power. So N, the number of compounded, so 12. T is in years. So this gives me $4,048.06. Okay. So the value of the account after 100 years, same thing, still compounded monthly. So I still do A equals 3,000, 1 plus 0.03 over 12. But instead of to the 10th power, I'm going to raise it times 12 to the 100th power. So this gives me $60,031.45. Make sure that when you put this in the calculator that you enter it exactly as written. You can either multiply 12 times 100 first and then raise this amount to that power, or you can put that in parentheses. So make sure you do that. Parentheses are your friend when you're working with calculators. All right, example 3, understanding continuously compounded interest. So consider an investment of $1 in an account that pays 100% annual interest rate for 1 year. The equation A equals 1 times 1 plus 1 over N to the N times 1 power equals 1 plus 1 over N to the nth power. This gives the amount in the account after 1 year for the number of compounding periods N. Find the value of the account for the number of periods given in the table. So 1, 10, 100, 1,000, 10,000, or 100,000. So we can see that when n is 1, okay, so you can see how the amount continues to go up. Over time, and you can see that curve kind of smooth out. Now, if you scroll in, it gets to be a very smooth curve. Okay. Notice that as n continues to increase, the value of the account remains very close to 2.718. This special number is called the natural base. So you can see that it gets closer and closer and closer, but it does get to that 2.718 number. So the natural base e is defined as the value that the expression 1 plus 1 over x to the x power approaches x as x approaches positive infinity. The number e is an irrational number. E equals 2.718281828459. You can see that it goes on forever. It's irrational, so it never repeats, never ends. The number e is the base in the continuously compounded interest formula. So a equals PE r to the t. So P is the initial principal invested, E is the natural base, R is the annual interest rate written as a decimal, and A is the value of the account after T years. All right, so let's try it. If you continued the table for n equals 1,000,000, would the value in the account increase or decrease? How do you know? Okay, so here's 1, 10, 100, 1,000, 10,000, 100,000. I can notice 2, 2.59, 2.7, 2.71, 2.718, 2.718. It's increasing, but it's getting smaller. Okay. So it does increase. The values increase each time the number grows. Example 4. Regina invests $12,600 in an account that earns 3.2% annual interest compounded continuously. Okay, so we're going to use the E. What is the value of the account after 12 years? Round your answer to the nearest dollar. Okay, so my solution. Use the continuously compounded interest formula with P equals 12,600, my initial amount invested, my rate of 0.032, so 3.2% change to a decimal, and T equals 12 years. To evaluate E to the 0.384, use the E to the X key on your calculator. So in this case, if you're using one of these calculators, so I'm using one of these calculators, I'm going to hit the math button. So this button right here. Okay, that's going to take me to this menu. I'm going to scroll to where it says log. And then the last one is going to be my option. So I would hit 4. Or you could scroll down and hit enter. Right, 4. So there's my E function. So when I do that, I get $18,498.63. Okay, so they did the 0.032 times 12, which gave us that 0.384 number. Okay, so to the nearest dollar, the value of the account after 12 years is $18,499. All right, so let's try it. You invest $125,000 in an account that earns 4.75% annual interest compounded continuously. What is the value of the account after 15 years? So again, I'm going to use that. Formula. So A equals my principal is 125,000. I have B to the 15 times 0.0475. So that's 0.7125. And this will give me $254,885.32. After 30 years, again, I'm going to use the exact same equation. The only thing that I'm going to change is instead of 15 years, I'm going to have 30. So this is going to give me $519,732.23. All right, example 5. Use 2 points to find an exponential model. Tia knew that the number of emails she sent was growing exponentially. She generated a record of the number of emails she sent each year since 2009. What is an exponential model that describes the data? So I write an exponential model in the form y equals a times b to the x, with y equal to the number of emails in hundreds and x equal to the number of years since 2009. Use the data to find the values of the constants a and b. So when data points have consecutive x values, the growth factor b is the ratio of their y values. So the growth factor for Tia's emails in the 2 consecutive years was 14/10. So remember, we did in hundreds. So if I divide both of these numbers by 100, I get 14 and 10. So 14/10 or 1.4. Okay, so it is an exponential growth. So I took the larger one divided by the smaller one. Okay. Use the value of b and one of the data points to find the initial value a. So y, we substituted 14 in for y, equals a times 1.4 to the 7th power. Okay, so that was this one, the 2016. Remember, from 2009, that's our 0 point. So 2009 to 2016 gives us that 7. Okay. I divide both sides by 1.4 to the 7th power. So a is approximately 1.33. So the function y equals 1.33 times 1.4 to the x models the number of emails in hundreds Tia sends x years after 2009. All right, let's try it. A surveyor determined the value of an area of land over a period of several years since 1950. The land was worth $31,000 in 1954 and $35,000 in 1955. Use the data to determine an exponential model that describes the value of land. Okay. So our formula is y equals a times b to the x power. Right? So 1950. So we have 1954 and 1955. Those are my 2 consecutive years. So we're going to say in the thousands. So 35 divided by 31. Which gives me approximately 1.129. So then I'm going to substitute that value in and find A. So I'm going to use, I'll use the 31. So 31 equals A times 35/31 to the 4th power, because 31 is 4 years after. That's in 1954. After the 1950. So I take that raised to the 4th power, and then 31 divided by answer. So this is going to be 31 divided by 35/31 raised to the 4th equals A. So it's approximately 19.078. Okay, so my final is y equals $19,078. 1 to the x power. Okay. This may not be the exact answer. If they used 35, they might have gotten a slightly different answer. So they probably used 5 and 35. You're close enough. So this is an exponential model that describes the value of the land. And again, it's at 1.13. They use 1.13. Example 6, use regression to find an exponential model. So Randy is making soup. The soup reaches the boiling point and then begins to cool. Randy wants to serve the soup when it is 10 to 15 degrees above the room temperature of 68 degrees. How long should Randy let the soup cool?
Randy is making soup. When the soup is done cooking, it is piping hot. Randy wants to serve the soup hot, but not too hot. How long should Randy let the soup cool before serving it if he doesn't want to serve it cold? To solve this problem, you need to know a few things. First, how cold is soup cold? If Randy lets the soup sit for too long, it will eventually reach room temperature, about 68 degrees Fahrenheit. Next, how hot should the soup be when it's served? Randy would like the soup to be about 10 to 15 degrees above room temperature, or around 80 degrees Fahrenheit. Lastly, you need to figure out how quickly the soup is cooling. Randy measured the temperature at various points over the first 20 minutes and recorded the data in a table. You can use the graph of the data to help in choosing an appropriate model. The graph shows the temperature decreasing as time increases. Let's try the simplest model first, a linear model. Here's the best fit linear model for the data. You can check how well the model fits by looking at the residuals. There is an upward curve to the residuals, so a linear model is clearly not the best fit. We could use a quadratic model, but a quadratic model has its own problems when put in context of the cooling soup. You can see that the revised model predicts the soup's temperature will increase rather than continuing to decrease. This does not make sense when talking about Randy's problem. Since the soup is cooling to room temperature, it should always be decreasing, but it also shouldn't go below 68 degrees Fahrenheit. So the model should also be decreasing, and it should have a horizontal asymptote, or lower limit at 68. One type of model that is decreasing and has a horizontal asymptote is an exponential decay model. So you can use an exponential function to model the change in the soup's temperature over time. A graphing calculator can help you create an exponential model for data using exponential regression. First, you need to put the data into a table on your calculator. Some calculators will only calculate exponential regressions for data values that approach 0. Even if your calculator does not require it, subtracting 68 degrees from the temperatures puts the information in the context of Randy's original problem, since how hot the soup feels depends on how many degrees above room temperature it is. Use the exponential regression feature to calculate an exponential model based on your data. Since Randy only measured one temperature at each time, there is no need for a frequency list for the data. Your calculator should give you the values for A and B in the exponential function, as well as some information about how well the model fits the data. When you substitute those values into the general form of an exponential function, f of x equals a times b to the x. You can use the graph of the function to find where f of x is between 10 and 15 degrees above room temperature. Tracing the graph of f of x, you can see that the soup cools to 15 degrees above room temperature at x equals 40 and 87/100ths, or about 41 minutes. And if Randy waits more than 48.5 minutes, the soup will cool below the 10-degree over room temperature target. You can translate the function vertically by 68 to see what the thermometer would read at a given time. Randy wants to serve the soup when the thermometer reads about 80 degrees Fahrenheit. You can use a table of values of the translated function to find what value of x gives g of x equal to 80. So, Randy should serve the soup between the 41-minute mark and the 48.5-minute mark, or about 45 minutes after he removed the soup from the heat.
All right, so according to the model in example 6, what was the approximate temperature 35 minutes after the cooling started? Okay. So here's my regression model, and I want to figure out after 35 minutes. Okay. Okay. So what I'm actually going to do is for x, because it was 35 minutes after the cooling started, I'm going to substitute that value in for my x value and solve. So when I do that and solve for y, I get 88.37 degrees. So on your calculator, so if you're using a calculator like this, in order to do a linear regression like we did in problem number 6, I enter my values. So the first thing that I want to do is actually click on list. Okay, here's where I can enter my values. So 1, 2, 3. Okay. Then I'm going to go to my second and then my stat button. Okay, so this takes me to this menu. I'm going to go over until I get to calculate. Okay, and then number 5 is my linear regression model. And that does it for me. So there's my values for A and my value for B, and that's my linear regression model. Concept summary. Writing exponential models. So general exponential model is y equals a times b of x. My compound interest is a equals p times 1 over 1 plus r over n to the nt power. And compounded continuously is a equals p times e to the rt. Okay. So general, a necklace costs $250 and increases in value by 2% per year. My initial amount is $250. My growth factor is 1.02. And the number of years x, so 250, so y equals 250 times 1.02 to the x power. The compound interest, a principal of $3,000 is invested at 5% annual interest compounded monthly for 4 years. So my principal is $3,000. My rate is 5%. My n value is 12 because there's 12 months in a year. And t equals 4 years. So a equals 3,000 times 1 plus 0.05, that 5% written as a decimal, over 12, raised to the 12 times 4 power. My continuously compounded interest. So same type of problem, except it's continuously compounded. So 3,000, 5% is my rate for 4 years. So a equals 3,000 times e. Remember, you can use that in your calculator, to the 0.05 times 4. That is the end of Unit 6, Lesson 2.